All right. Hello, everybody. Can everybody hear my microphone? Is my mic working for everybody? Okay, great. Great. How was your guys' first term test? Was it good? Was it bad? Will the recording be posted? Yes, I will post the recording, or AMACSS is going to post the recording of this review seminar, probably tomorrow or today. Yeah. So, anyways, if you haven't known by now, my name is Edison Pham, or you can call me Eddie, and welcome to C11 Term Test 2 Review Seminar. And as for AMACSS, I'm pretty sure you guys know what AMACSS is, but just in case, here's the link to our website, our Instagram, and our Discord. And what we do is that we do review seminars for basically any course. All right. And just a disclaimer, none of these questions are really are not like a reflection of what's gonna be on the exam exactly, but hopefully it'll help you guys go through the exam much smoother. Anyways, let's get to the questions. Will the solutions be? Yes, they will be. I already have the solutions created. I'll post them on the AMACSS Discord server, or I'll also post it at the end of this review seminar. All right, for the first question, true or false? When a decision tree is fully grown out, the entropy in each leaf is zero. Any answers? Can you explain why it is false? Can have other stop. Oh, sorry. Um, I forgot to mention there's no stopping conditions. So when it's fully grown out, it just keeps on growing, growing, growing until there's like one class in each leaf. That kind of gives it away. Because if we set the stopping condition to be less than it should be. Yeah, but in this case, the decision tree is fully grown out. So each leaf would have, let me bring up the whiteboard. So each leaf, actually, yeah, then it's true, exactly. Because when your decision tree is fully grown out, let's say this is the leaf node, right? Then in this leaf node, there's only one class. If there's one class and we calculate the entropy of this leaf node, let's call it D. Wait, this brush is not good. Hold up. Or I can zoom in. This is equal to the summation, negative summation of from n, I equals 1, 10, p of xi, and log p of x. Sorry, I gotta move some stuff away. Like something like this. But if there's only one class, then that means the entropy is just this of this particular class. However, the probability of observing that class when there's only one class, guess what it is? It's exactly one. But then one inside of the log is zero times zero, and then we just get zero. So the entropy is zero. All right. Whoops. Next question. I'll give you guys 2 or 3 minutes. I'll give you guys like 3 minutes for this one. What is the upper bound of the entropy of x, where x is a finite, discrete, random variable? So x can only take up finitely many values as a random variable. So I want you guys to find what's the maximum possible value this entropy function can reach for given x. Does that make sense for everybody? Sorry, does anyone not understand this question? Okay, I'll give you guys until like 5:17. Does anyone have an answer? Yes, exactly. The upper bound is the log of the number of x's. And how did you get that answer? Actually, what random variable x should it be such that the entropy is maximized? Do you know? Think about what the entropy function measures. It measures the randomness of a random variable. So what finite discrete random variable is completely random? What's the first thing that comes to your mind? Evenly spaced. That is correct. Not necessarily independent. This is one random variable we're talking about. Yes, that's correct. Evenly spaced. So for what that means is that the random variable is uniformly distributed. So how do you prove this exactly? Well, in C11, if this was ever asked on an exam, you don't have to be rigorous, but I'll show you why it's the case. So you have the entropy of, not the entropy of X. We know by the formula this is equal to, and I'm using the positive version of it, just so that you can see what I'm about to do after. 1 over P of xi. This, you can write this. Remember, entropy can be written as the expected value of the log. I'll leave it as an exercise for the readers, just to see why this is the case. But it's pretty simple, I think. Sorry, this is the actual random variable, not just one point from it. But then, if you recall from Stabby 52, you don't have to remember this. This is less than or equal to, we're using the Jensen inequality right now. The log of the expected value of 1 over P of X. However, what's the expected value of this? This is just simply equal to the summation, all in this big bracket right here, the summation of P of xi times 1 over P of xi. Cancel, cancel, and you just get the log of summation of a bunch of ones. How many ones are we summing up? N ones. Just becomes log of n. The number of states which the random variable could take hold of. All right? So that's the answer to that question. Let's go for the next question. I'll give you guys like 10 minutes for both of these questions. It's going to take you quite a while for this one, but oh, by the way, are you guys covering KL divergence in the exam? Did she say you're going to do something with KL? Does anyone know? I'll take that as you guys don't know. Anyways, if you guys remember the formula for KL divergence, use the definition of KL to prove this identity. And yes, this is an identity, not a definition of mutual entropy. She taught after logistic regression. Okay, that's good. And you probably haven't seen this before, but you essentially, this is joint entropy. You treat this as like a random vector such that you can do this. So instead of just p of x times log of 1 over p of x, is p of xy times log of 1 over p of xy. So use that definition to prove this identity. I'll give you guys until 5:30 for that. What is I of xy? That is mutual entropy. No, sorry, mutual information. Or what you guys would call it is information gain for decision trees. Yeah, information gain is what we call it for decision trees. What it's actually called is mutual information. She posted this in the notes, I believe. All right. I hope that was enough time for everybody to try out the question, but let me solve it. I can screenshot it. All right. For the first one, I'm just gonna do from 1 to 2, just because 2 to 3 is pretty easy. You just have to change one thing, and that's about it. So let's see. Mutual information of X and Y. Recall that the definition of it using KL diversions is the following. Sum of I and J, P of X, I, comma Y, J, times the log, and the ratio is the full distribution, the full probability, the joint probability divided by P of X, I, P of Y, J. And now the trick here is to notice that there's not really a trick and consider this probability in the numerator. This probability is simply just, it's simply just this condition on J times P of Yj. And once you do that, this cancel out. And now what you're left with is simply just this. P of, you guys know what's already in here. The log of P of xi, condition on yj, divided by P of xi. Using logarithmic properties, you can break this up as the following. Whoops. P of the joint probability times the log of the conditional yj minus, because it's in the denominator, the sum ij, P of something, log, and then let me see if I can fit in the screen. Log P of xi. Notice this, by definition, since in here we have xi comma yj, we essentially have to marginalize over y because this term is constant over y, but this term is a probability. So when we sum up all the j's, we essentially are left with the sum of P of xi times the log, the negative, sorry, the negative summation of P of xi times the log of P of xi. And you guys know this is just h of x by definition. Also, by definition, this is equal to the negative h of x given y. So altogether, this is equal to h of x minus h of x given y. So how do we change it so that this is h of xy minus h of xy given x? Well, simply, instead of conditioning x with y, we condition yj xi with x, P of xi. And then this term would cancel out with that. So that's literally how you would do the other direction. As for the next one, like I said, you have to write it as treat this xy as a vector, a random vector. Sum of ij, P of xi, P of yj. Actually, we can throw out the negative for here. Log P of xi, yj. Now, this is equal to, so we can do the same trick, turn this into a conditional probability. Xi comma j P of X, let me see if I can save space here. P of Xi, Yj, log of P of X. Oh, someone joined. I given Yj times all big bracket Yj, like that. I can fit the bracket in there. And then we do the same thing. We split up the summation like this. P of Xi, Yj, log P of Xi given Yj. Don't forget the negative sign. And then since this is multiplied, we have to also just subtract because we're disturbing the negative sign. Like this. Yj. Yj. And then you can simply observe this term right here. It's just h of x given y. And then we need to do more work here. So once again, what I would do is that I would marginalize over x because this term is constant with respect to xi, but this term is just a probability, like I said. So for this term, we marginalize over x. Yi log p of yj. Don't forget the negative sign. And this, by definition, is equal to the entropy of y. But recall from our previous definition, the entropy of y, if you rearrange it, this is actually equal to the mutual information of x and y, plus, if I can fit it in here, actually, let me clear the board. If we fit all of this, sorry, anyways, h of x, h of y is equal to mutual information of x and y plus h of y given x. And then if we put everything together, we just have this. Because remember, we also had another term, h of x given y. And we're done. So that's how you would prove these two identities. All right, for the next question. Given two random variables, what do you guys think is the upper bound of their mutual information? Hint, use the identity we just proved previously. Remember, entropy is, you prove this in your assignment, it's positive. So think about what's the upper bound of this. Yes, I will post the solutions to all the questions, except the bonus ones. So can anyone tell me what you guys think is the upper bound of this? It's got to do with something with the conditional entropy. This and this. Does anyone want to take a guess? Nobody? All right, then. The upper bound of mutual information of x and y is actually just simply because sorry, let me remove all of this first. The upper bound is simply just it's less than or equal to the max of the entropy of x, comma, the entropy of y. And this can only occur when one of the random variables, x or y, completely explains the other one. So think about, actually, I'll go to the next part. Describe what happens, describe this in the context of decision trees. So remember, mutual information is basically the same as information gain. So in this case, we're maximizing our information gain. Can anyone tell me, or can anyone describe to me what is this in the context of decision trees? Anybody? Just a guess. Huh. All right then. So child node is pure. Uh, yes. That is correct. So when you essentially maximize the entropy, in this case, when you get something like this, you're basically perfectly separating the classes. So let's say we have a bunch of X and O's. This is what it is. So the entropy is like pretty high for this one. However, when you split it to XXX, OOO, we're basically, by doing this split, we maximize the information gain. So that's what it is in the context of decision trees. For the next question, given random variables X and Y, remember they're independent. What is the information gain, sorry, the mutual information of X and Y? Remember, it all comes back to this identity right here. If the information of, if X and Y are independent and you have the entropy of X given Y, Y doesn't really tell you anything about X. So it's just, yes, exactly, it's just zero. And can you describe to me what this means in the context of decision trees? Or rather, let me give you some intuition. When your random variables are independent, the information they share is nothing because knowing about one random variable, X or Y, does not tell you anything about the other. So I'm actually going to just give you the answer. So what this means in terms of decision trees is that your split is essentially useless. All right. So I don't know if you guys remember the formula for information gain. One of the child node has all of the elements, the parent node. The other one has none. Not quite. If actually, I think yeah, that would work as well. That is true. Yes, you're correct. So correct me if I'm wrong, but I believe the formula for information gain for the current node is this TK, where TK is some split, is equal to H of D minus, I believe it's my H of D given TK. So the entropy of the after you apply the split. However, if the split is completely useless, then basically it does the same thing. It doesn't really do anything. Is the slides posted? I will post them on the AMACSS Discord. But anyways, if you apply the split and it does nothing, then you just get the same entropy as is. So you just get zero information gain. The split is completely useless. I'll skip the bonus question. I'll leave it for you guys to do because it's pretty fun. For this next question, I'll give you guys, I think 10 minutes will be fair for this question. Yeah, I'll give you guys 10 minutes for this question. So assume everything is in log base 2. Calculate h of y, the root node of the decision tree. And also find the optimal split after the root node. So you have to find all the possible splits, calculate the information gain, and pick the one with the highest information gain. All right. Also, if anyone has any questions, please do speak up when I'm going. All right. I hope that was enough time for everybody. Sorry if you did not have enough time to do the question, but I'll go straight to the answer. All right. So for the first one, we have to calculate the entropy in the root node. So H of D, it's equal to 1, but I'll show you how you get it. So we write out the entropy formula, log base 2, by the way. And then we also have P of y equals 1, log base 2, P of y equals 1. And this is just equal to negative 4 over 8 log is 2, 4 over 8. And likewise, this is just, this here is just 1 minus P of y equals 0. So that's the same thing. And when you combine these together, you would get 1. Is that correct? Did everyone get the same answer? Cool. Nice. Good job. All right. For the next question, I want to ask you guys how many decision stumps or how many possible splits did you guys get? Just type in a number in the chat. 1, 2, 3, or 4, or 5, or 6. Did anybody try the question? Geez. All right, I'll just tell you. 5. Yes, you're correct. There is 5 splits. So the first split is we're checking if x1 is greater or equal to 65? Question mark. Yes or no. Tau 2, if x1 is strictly in between 30 and 65? Yes or no. Tau 3, is it between 18 and 30 inclusive? Yes or no. And for the next ones, tau 4, which relates to x2, is x2 equal to a? Yes, no. And I believe it's a or b. Yep, it's a or b. But we don't have to include the decision split for b. Because start of the root node, if it's not a, then what is it? It's b. So we don't have to create the split for that. And finally, whoops, tau 5 is x3 equals to m, or you can do it for f as well. It doesn't matter. Yes or no. All right. And just because I might not have enough time, I'll just do like one or two just to show you how to do it. So let's calculate the information gain if we apply split 1, tau 1. Then that's just simply h of d, which we are given, minus NL divided by N, the entropy in the left node, minus NR, the number of elements in the right node, divided by the total elements, times the entropy of the right node. So we're given that this one is equal to 1. But how about this one? It should be equal to, actually, let me split this work up. Could you explain why we cannot do BC? Oh, sorry, did I only include, was there like C in it? There's no C. For X2, yeah, there's no C. There's only A or B apart from A. You're good. Oh, all right. No problem. So if we write this all out, This is equal to 4 over 8. And then a trick I like to remember is that it's this. This is a trick I'm giving you guys. So 4 goes in the denominator and then in the numerator, like this, for all of these ones. 4, because we're taking this one and putting it down here. 4. And then for this, we literally just count from the graph. So, sorry, from the table. And I believe tau 1 is this, and this. If we split it by this, then we have 1, 2, 3. Wait, did I make a mistake in my calculations? No, I didn't. So out of all of these, there's 4 out of 8 when x1 is greater or equal to 65. And from there, if we take like a subset of these, only 3 of these have ones. Only 3 of these have ones. And then literally from here, we just take 1 minus of this. We take 1 minus. So that's kind of like a cheat code. And for this one, this term right here, you take 1 minus this. So it's the same thing. And then you proceed as usual. 4 log base 2. 4 plus 4 log base 2. 4. Then you do the counting thing again. So here's what you would get. Oh, yeah, I changed up the question just because I thought it was a bit too, it's gonna take a bit too long. Yeah. Did Irene post my slides, perchance? I think Irene did post my slides. Ignore those slides. I have an updated slides that I'll post on AMACSS later today. All right. And then simply you get 0.1887. That's one of them. For the other one, another important one I want to show you guys is this one. I think it's for information gain of D when you use the split tau 3. This one is a bit different. Minus. Okay, I think you guys get the point. You guys know what comes here. So h of D is equal to 1, but then uh we have actually I think it might be important if I write it out. DL and then minus h of dr. So this is equal to 2 over 8. But what about the entropy of DL? What is the entropy of DL? Notice that if you take a look at the table, I think we're splitting by this. So it's going to be 2 over 8, 2 of these out of 8. But then in these ones, it's only zeros. So it's a pure node. What do you guys know about pure nodes? Type in the chat. What do you guys know about the entropy of H of DL if it only contains one possible class? No entropy. Exactly. So it's just 0. This term gets deleted, and then you would continue on with your calculations for H of dr. And I'm just going to give you all the answers at once. Actually, this is equal to 0.31, etc., etc., etc. So I'm just going to give you all the answers. Actually, I'll post the solutions later so you guys can refer to the answers from there. But those were the important ones I wanted to show you guys. All right. The next question. Describe overfitting and underfitting in the context of decision trees. I think we kind of already went over this, but let's start with overfitting. Can anyone tell me what overfitting looks like in the context of decision trees? Tree is too deep. Exactly. Can you be a bit more specific? Let's talk about the leaf nodes of the tree. What can you say about the leaf nodes? Only has one sample. It could have like two samples because when you're at two samples, you can't really make any more splits from there. Or could we have three, four, five, as long as it's like a pure node, when each leaf node is completely pure. And when that happens, that means one of those leaf nodes could be like noise, right? So that's what it is like when it overfits. Underfitting. It's, as for underfitting, it's kind of like the opposite effect. Can anyone tell me what underfitting looks like in the context of decision trees? Remember, the deeper your tree, the more complex it is, the more complex structure it has. So what happens when your decision tree underfits? Yes, exactly. When the entropy of each leaf node is way too high, or in this case, when your tree is not deep enough. That's what happens when your decision tree underfits. Can anyone tell me three ways to terminate a decision tree algorithm? So we want to do this because sometimes your decision tree will overfit and we need to take remedial measures. Can anyone just give me one way to terminate a decision tree algorithm? When minimum number of leaf node is reached. Correct. When entropy is zero. That is also correct. Any more guesses? Or actually, th those guys got it right. Any more answers? All right. So what I have written down is that you can terminate it. Information gain is too small. Exactly. Yes, that's absolutely correct. When your information gain is too small. And when your information gain is too small, that means that your decision stump split makes little to no difference at all. So just creating an extra leaf for no reason. So what I have written down is you terminate by a maximum depth. So I don't know if you guys done or I don't know if you guys use sklearn, scikit-learn, but there's like a for random forest or decision trees, you can threshold it by how deep your trees are. For number two, you can terminate by information gain, as some of you guys mentioned. When your information gain is extremely small, so your split makes no difference. And actually, when your information gain is small, that means your h of d, actually, I'm going to show you visually. That happens when your h of d, h of dj to be specific, minus h of dj given the split. When this is small, right? When this is small, sorry if I'm abusing the epsilon notation here, then that means these two are very similar. And what happens when these are similar? This split is practically useless. And all right, and the last one is minimum sample by split, so that this ensures that each leaf node would have at least, say, 10 sample nodes in it. Because if you only have like one sample node in it, then that's not really a generalization of the population necessarily. That could be like noise. All right. All right. Question one, can anyone explain to me? Oh, and also, by the way, we'll have a break at like 6:30. Can anyone explain to me the difference between classification and regression? I believe I discussed this in the previous review seminar. There's two main keys to classify a classification algorithm and a regression algorithm. Yes, discrete. And what else? Correct. Regression is continuous. However, remember in the previous review seminar, if you were there, I showed cases where your classification could also take in like continuous numbers as well. But in that case, it's not a classification algorithm. So what was the other condition that we need for both regression and classification? Think about the loss function. Ordering, yes, exactly. So you need to mention that ordering. There's no ordering in classification, and there is ordering in regression. Excellent. Nice. Suppose in binary classification tasks, you observe the objects are linearly separable. Is it a good idea to use linear regression? Explain why. What do you guys think? Is it a good idea to use linear regression for binary classification? Depends. I'm talking like in general. Linear separable means it can be split up with a line. Oh, someone has their mic on. You want to answer or not? No, still penalty for correct classification. Uh, sorry, one of you guys have your mic on. Suchan Leo.
Oh,
Yeah,
sorry.
all good, all good. So the reason why you don't want to use linear regression for classification problems, say you have like X and O's like this. And let me see if I can draw a sufficient depiction. Notice when you're using linear regression, you're basically comparing like everything above this line classifies as X. Everything below this line classifies as O's. So that's essentially what linear regression does in terms of classification. The reason why you do want to do this is, let's say you have something like close to the middle, right? Something very close to the middle. So let's call this like 0.49 and like 0.51. It treats this misclassification, assuming that your decision boundary is at like 0.5. It treats this the same as this 9001, 0.999. So clearly this error, this misclassification, so this is like your y, and this is your y hat. It treats every single misclassification as the same. So if you have like a large misclassification, it treats it as the same as a very small one, which is not good. And you can see this visually with the graph here. You have an X row over here and like an O over here. It'll treat these two misclassifications the same as this one and this one. So that's not a good thing. And also, this was like a previous exam question from my midterm. If there's low to no chance of misclassification, is is there's low chance? Personally, I wouldn't do it because just simply because there's much better ways. But like in general, you would not use linear regression for classification. People did that in the past and they realized that's not a good idea. By the way, for the next question, I'm pretty sure you guys should have talked about Voronoi tessellations, right? It should be in the classification chapter, right? Did any of you guys do Voronoi tessellation? Does anyone know what a Voronoi tessellation is? Yes, it's the diagram. So I don't know if I have the notes on right now, but I'll actually give you guys like 5 minutes, actually 7 minutes to do this question, just so that you guys can pull up the notes and figure out what the Voronoi tessellation is. So I'll give you guys until let's say 6:20 to do this question. And also this is for 1 and n. So we're comparing it to the closest neighbor, not necessarily the second or third. All right. I hope that was enough time for you guys to read up on what a Voronoi tessellation is and do the question. So just to give you guys a brief idea, the Voronoi tessellation diagram is essentially if you have, whoops, if you have X, O, O, X, X, stuff like that, it basically draws like it's a way of visualizing like the decision boundaries of K and N. So it looks something like this. And these are like your axes. All right. So the question tells you to find the Voronoi tessellation diagram for these set of nodes, set of points. So let me take a screenshot of this really quickly. Put it right here. Now, let's draw the diagram. So we have from 0, tick, tick, 1, 2, tick, tick, 1, 2. At the origin, we have an X. Probably be better if I did it in red so you guys can see better. And then the other X is at 1, 1. For the O's, we have an O at 1, 2, an O at 2, 1, 2, 1, and another O at 0, 2. So how this decision boundary works is that whenever you add a new point to your data set, then let's say it's right here. Then what's the closest one? It's this one, the X. So we will classify this as an X. And this diagram basically helps us visualize this decision boundaries. Now, the thing about this question is that I'm pretty sure it's either going to show up on this exam or the final, because it usually would show up on the exams. And people tend to get this question wrong. I'd say it's like, if you know how to do it, it's like free marks basically. So how you would do it, start with this one. Look at all the opposing nodes. You draw just a small decision boundary between these. Start with this one, look at the other ones. Oh wait, there's you can draw like right here, right? But this one, it's already covered by this barrier looking thing. And then you just try to extend the lines like this. You can think of it as like extending the lines. But then this part is like we don't we don't worry about this part because this line extends past it. So this is how you would this is how you would draw the Voronoi tessellation. Anything that goes into this region right here gets classified as O's. Anything in this region right here gets classified as X's. So that's kind of a trick I'm giving you guys to do this question. One of the benefits of coming to the review seminars. All right, that should be free marks on the exam if it shows up. For the next one, it's a multiple choice. Actually, true, false. Um, the first one, true or false. Bagging methods reduce the variance of your model. Can anyone tell me if it's true or false? If it's true, explain why. Yep, you are correct. Can you explain why it's true? CLT. You have the right idea. You actually have the right idea. You can actually treat decision trees as like random variables. I think there's like research papers made on this. And one of the profs at U of T is doing like research on this, but you can treat these decision trees as like random variables. And what bagging does is that we're essentially getting like an average of all these models. So as we increase the number of decision trees and we average it out, and then we take like some very arbitrary data point and put it into the model, then it's going to be a lot more robust. So we're essentially, yes, we're decreasing the variance of the model. I think, do you guys want to see? Actually, no. It's showing you guys it was like not related to this course. Anyways, the next one, Random forests and decision trees are sensitive to small changes. True or false? Yes, you are correct. Only decision trees are sensitive to small changes, just because a decision tree is simply just one decision tree. But the reason why this is false is because we have random forest in there as well. Random forest is a bagging method. Therefore, it is much more robust to small to um to small changes. Even big changes as well. It's also robust to big changes. Actually, let me go back to this and I'll show you why. So recall from stab B52, you had or stab B57 you take it. Your sample variance is this. Your sample variance is this. And your sample mean is this for x1, x2, xn. Follow some distribution. As we increase the number of n's, your sample variance, what does it approach? It approaches zero. Whereas your sample mean converges in probability to mu. All right? So that's the reason why. All right. Increasing tree depth will never cause RF to overfit, thanks to bagging. True or false? Yep, you're correct. Can you explain why? Or give me like the rough idea? Think about if we increase the tree depth, let's say we increase it to like full length, full depth tree, then each node would have like pure classes in it, and one of those classes could be noise. Yes, exactly. So if each of these decision trees overfit, then the average of it would obviously overfit because we're essentially like let me just show you why. If decision tree one, if decision tree one has like a bunch of noisy fits, decision tree two has a bunch of noisy fits, then if we take like the average of it, then our average would be extremely noisy. There's nothing about the formula to get the average of it that suggests that it would decrease the sensitivity. So actually, from this one, it would bagging methods do decrease variance, but like in this case, if we have a tree depth too big, then obviously it would overfit. And finally, KNN does not require training time, but rather testing time. True or false? True. You're correct. And I'm pretty sure you guys know the reason why for this, but the reason why KNN doesn't require training time is because, well, that's how the algorithm is. It's a lazy learner. But the trade-off of that is that all the time that it takes to learn is in the testing time. So we reserve the whole entire data set. And when we do that and calculate all the R2 or the Euclidean distances between our new points, let me draw it. Our new points and the other points, as such, get the KNN distance. This would take up a lot of testing time in opposed to training time. We're not training a model. We're not saving any parameters to KNN. All right. All right. So it looks like we're at the 6:30 mark. Do you guys need a break or do you want to continue on? I'll give you guys like, if you guys want a break, I'll give like 10 minutes. Otherwise, I can continue. So, yeah, break. Do you need a break? Okay. All right. I'll give you guys 10-minute break. So I'll see you guys back at 6:40 p.m. All right. I'll type that in the chat or right here. See you guys till 6:40 p.m. Great. All right. Make this bigger. Oh. Serve quick question. The reason why there's no splits between is because 0 is the smallest neighbor of. Uh, there's no split between 0, 0. So the origin and 2, 1. Well, it's because if we have an x here and x here, this x already accounts for all of it right here. So if we have like a 0 right here, then this decision boundary would like overtake the decision boundary right here. Does that make sense? Actually, you are somewhat correct. If we extended this line to like very, very long distances, then it would look something like this. So you are actually correct. There would be like this decision boundary right here that overtakes this one. All right? Sounds good?
Yeah, I think it's okay.
All right, perfect.
Yeah.
And that's one thing I have to change in my solution sheet. All right. I hope you guys had a good enough break, and we will continue with the review seminar. All right. I believe we're here now. Question 5. Explain the primary difference between discriminative and generative models. If possible, give me some examples. Can anyone tell me the difference? Or how about, can anyone tell me what is a discriminative model and what is a generative model? Let's start with that. Models directly posterior. Yep. Learning the conditional probability, discriminative, and the joint probability. So the full distribution. You are correct. More particularly, a generative model is called generative because with generative models, we can generate new data points. For discriminative models, these models essentially focus on learning the decision boundaries, particularly just through the conditional probability. So that's why it's called discriminative, because it discriminates the classes with a decision boundary. Can anyone tell me some examples of a discriminative model and generative model? This is a pretty common question in this variant of this question is pretty common in exams for Irene's exams and David Fleet's exams. Can anyone give me examples? Yep, you are absolutely correct. Canon, RF, logistic are discriminative. Yep, everybody is correct. Question 6. What is the key assumption in, actually for this one, this is a whole entire, for this one, I might actually have to give you guys like 10 minutes. This was a whole entire question on my exam when I took it for term test 2. Actually, let's start with the first one. What is the key assumption in logistic regression for binary classification? Does anyone remember? Yep, the decision boundary must be linear. The reason for this is that so we can do this the following. We have like the log of, I'm not going to spoil what's going to be in here, but it's like the ratio of like the probabilities. And this is equal to like W transpose xi, where xi is like the vector of the data plus the bias term. So we have to assume this in order to like have like the decision boundary. Is it greater or equal to 0? Oops. All right. So the next part is write the conditional probabilities of the class labels given the input features. Whoops. Uh, given the input features in terms of the decision boundary. So I just showed you guys the decision boundary. It was like some logarithm, and use that to derive and name the objective function of the logistic regression. So what do I mean by name? The loss function for logistic regression is a special type of loss function. So not MSE, not mean squared error, not mean absolute error. It's something, and you have to figure it out. So for this section, I'm gonna let you guys do this for like 10 minutes. So give you guys until like 6:55. Yep, 6:55 to do this part. All right. I hope that was enough time for you guys to at least try out the question. So before I take out the answer, can anyone tell me what was the name of the objective function for logistic regression? Does anyone remember? Anybody? Sigmoid function. I'm talking about the whole entire objective function. Yes, that is correct. Cross entropy loss. You use cross entropy loss for classification. To take up this solution, I'll do that right now. So, essentially, since logistic regression is like a discriminative model, we want to model, and essentially we're doing like binary, and we want to model this and this. So given x1, and but then notice this is just if we let this equal to like p1, this is just equal to 1 minus p1. So we just have to find p1 as the parameter. And to do this, we want to compare like the decision boundary P1 divided by 1 minus P1. And recall this is like linear decision boundary. We want to see if this is to z greater to 0. If it's greater to 0, then we classify it as P1. Otherwise, we classify it as P2, which is 1 minus P1. So to find this parameter right here, which happens to be your posterior, we can simply apply Bayes' theorem. So P1 is equal to P x1 to n given y is equal to 1, P of y, that's your prior term, and your evidence term. This is proportional to, because we can omit this evidence term. This is proportional to, and then we can break this up, assuming independence. P of x. Actually, no, I don't think we're allowed to assume independence, so I'll just continue out from here. Wait, hold up. Actually, we're not supposed to get rid of the evidence term. So unfortunately, we have to continue on from here. But then you can write this as P of x1 given y equals 1, P of y equals 1 plus x1 given y equals 0, P of y equals 0. Because remember, this is the same as marginalizing, undoing the marginalization of the y's, and then applying conditional probabilities. And now what you want to do next, you want to divide the numerator and the denominator by this. So you would get, so this is actually equal to 1 plus P of x1 n y 0, P of y is equal to 0 divided by same thing, but you have y equals 1 instead. All right. And now, if you want to write this in terms of the decision boundary, you can write, you can let the decision boundary given this, oh, given your input as the following. Log or ln, I'll just choose ln. And given y equals 0. I also want to mention, it doesn't really matter if you want to compare like if if y equals 0 is in the numerator or denominator, as long as this decision value is like less than or 0 or greater than 0, you basically have your answer to what the prediction is. And yeah, so that's literally all you have to do. And let me clear up this top part to finish up the question. And with this, finally, you can write P1 is equal to 1 over 1 plus. And then you do e to this decision boundary. So that's how you would write it in terms of the decision boundary. So what's the next question? Right, conditional boundary, decision boundary, did that, and use that to derive and name the objective function. So as mentioned, the name of the objective function is the cross entropy loss function. So let me clear up the board really quickly. And to derive the loss function, we start with P of W, where W is like the weights. In this case, it's a vector. Y1, your classes. So essentially your data set. This is equal to P of Y1, 10, W, comma, W vector, comma, X1 through N. And then you want to apply law of conditional probabilities twice. So you get W vector condition on X1, the probability of this. And you can verify that if you combine these two together, you get P of W vector and X1 through N. And then when you multiply together, this essentially becomes the full joint probability. Then the denominator, you can apply the same thing. P of X, sorry, it's the full distribution. But then this denominator is the evidence term, so you can omit that. Get P of Y, 1. You just get the numerator up here. And if you take the negative log of that, this is proportional to optimizing negative log of whatever this is. Also got to mention, this term is also constant with respects to W. So this term disappears and this terms disappear when you put everything inside of this bracket right here. All right. So what you have now is that you have P of Y1 through N, W vector, X1 through N, P of W vector to N inside the log. And obviously, we want to assume, actually, first we want to assume that the prior is uniform. All right. So the thing is, if we already know W, then that means we already know X1 through N. So what we can do is that this is just equal to P of W, but P of W is uniform, right? So let's say it's equal to like some constant C. But by assuming that this is proportional to, after applying log rules, just P of Y, W vector, X1 through N. Okay? And then you can just simply apply, let me clear this, the following. This is equal to the following. Negative log, the product of all the probabilities. P of yi given W vector xi, and this is just equal to the negative summation of, actually, I'm skipping too many steps. I'm gonna take this, and this happens to be equal to P1 yi, 1 minus P1, 1 minus yi. The reason for this is that if y is equal to 1, then obviously we want to classify this as like P1. If y is equal to 0, then this becomes just 1, and we're multiplying by this. This is the probability corresponding to y equals 0. This is a probability corresponding to y equals 1. So that's pretty convenient. And then we plug everything together. We finally, and also applying log rules as well, we get the following function. Log pi, sorry, P1 plus 1 minus yi log of 1 minus P1 from I equals 1 through N. So yeah, this is how you would derive the loss function. If it ever shows up on the exam, you guys would know how to do it. Okay, for the next question. Describe the shape of the GCC decision boundary for binary classification. Can anyone tell me what the decision boundary for, sorry, someone's trying to join in. Can anyone tell me or describe to me what the decision boundary shape for GCC is for binary classification? This was also a past exam question where they asked you what was the shape of the decision boundary. But you can essentially think of it as like, think of the formula that she derived in class. Let me see if I can write it down. Uh, I believe let's see. It's a pretty big formula, so just bear with me. -1/2, log of absolute value of first. Actually, it's important to note that the first class follows like a its own Gaussian distribution, and so does the second class. So you would get this formula, mu1, I suppose, sigma1 inverse, vector minus mu1. And then for the other one, we want to subtract this. And this is for the second one, second class. Sorry, this is supposed to be sigma 2. And notice that these are quadratic functions. And when we essentially want to compare, notice this is the decision boundary. Whoops. This is the decision boundary. And yep. And we want to see if this is greater or zero. But the decision boundary happens at alpha of x vector is equal to 0. So the decision boundary in this case is either elliptical, quadratic, or linear. You guys have to remember that because it might show up on the exam at some point. All right, question 2. What's the key assumption of naive Bayes? I'll give you guys a couple of seconds to determine. Features have no correlation. Features are conditionally independent given the class labels. That is correct. So yeah, that's basically all it is. What it's saying is that, let me show you. P of F1 given C, the class label, this is just equal to this. It's important that you guys mention that features are conditionally independent given the class labels. Saying that the features are just conditionally independent is not sufficient. And more importantly, independence does not actually correlation does not is not equal to independence. So do not say that the features have no correlation. All right, so whoops, this is supposed to be just I. So this is what it's saying. All right. For the next question, this is also a past exam question, though I changed the data set up a bit. I'll give you guys like uh, 10 minutes. Yeah, 10 minutes to do this question. It's important that you guys get used to writing these questions pretty quickly because in my exams, it was originally designed for like 1 hour, but we got like 3 questions the same length as this one and the decision tree plus 2 pages of multiple choice and the short answer. And we had to finish it in like an hour. So, but we were lucky that she gave us like an extra 30 minutes. So I'm gonna give you guys like 10 minutes. Hopefully you guys can do this pretty quickly. Oh, do we need to add the smooth term? Sorry, can I ask, what do you mean by that? Do we need to add the smooth regularization term?
Like for some conditional probability, it might be zero because there's no observation there. But
Oh,
just wondering, yeah,
for now, just don't include that. If one of them is zero, just write it's equal to zero.
thank you.
All right. I hope that was enough time for you guys to do the question. I'll only take up the solutions for the prior, but I can show you guys like a trick of solving for the conditional probability so that you guys can use it during the exam. So, actually, first of all, can anyone tell me what the prior probabilities are? Let's start with P of y equals 0. What is that? Come back to the question. What is P of y equals to 0? Yep. How about P of y equals to 1? Yep, 3 over 8. And P of y equals to 2. I'm pretty sure. Yeah, it's also 3 over 8. Perfect. So for this type of question, there's like a high likelihood that you're going to get it on your exam. What I would do is that I would count how many, consider all the labels. Actually, it'd be better if I screenshot it and show you guys how to do it. So just to keep things organized, what you want to do is consider writing like x1. So this is like your conditional probability. But then you want to fix y equals 0. But then you want to also consider, sorry, x1 is equal to like how many states are there? There's one, two, three possible states. So it's when x1 equals 0, and you want to fix y equals 0 in this case. This is equal to something. Do the same thing for x1 is equal to 1, given y equals 0, and so forth. And then you would do that for y equals to 1, p of y, x1 equals to 0, y equals to 2, and so forth, so forth. Does that make sense? Essentially, this row, if we're going this way, we're changing this. If we're going downwards, we're changing the y's. But then with the y's, you need to remember that the denominator for this one, the denominator of each row is the same. So in this case, P of x1 equals to 0 given P of y equals 0. Let's count. It's two instances when y is equal to 0. Okay? So this would also be 2 divided by 2. P of y equals to 1. There's 3 instances, so it's divided by 3. P of y equals to 2. There's also 3 instances. And from those instances, you would literally just count how many of these, so 0 and 0, have class 0. So one, just one. This would be 0 because there's none. We only have like 0 and 2 pertaining to the y class 0, and this would be 1. So that's how you do it. Where's my mouse? And then you would do the same thing, the exact same thing for x2, which is the culture in this case. x2 equals a given y equals 0. That's equal to. And you would like copy and paste the denominator because it's 2 here. Let me draw this line. 2 over something. P of x2 equals to b given y equals 0. So forth. It's to 2. Sorry, divided by 2. All right. So the whole thing about this, whoops, where's my mouse? Is that you want to keep it as organized as possible so that you don't miss calculations or repeat calculations. You do the same thing for, God, where's my mouse? For x2 equals to a given y equals to 1, x2 equals to a given y equals to 1, y equals to 2. Then you just copy and paste this number right here. Just copy and paste, and so forth for x2 equals to a, b, and c. So that's how you do this type of question. For the next question, it's a bit tougher. Not many, I don't think a lot of people got that correct in my exam. For naive Bayes assumption, how many parameters do we have to learn? So let's start off with the priors, because first of all, ultimately we want to learn, if I remember correctly, we want to learn this, right? We start off with this, but then we can decompose this into P of x1 given x2, see, times P of x2 given c. So this is something we have to learn. This is something we also have to learn. But we also need to learn the prior term as well. So to do that, let's start off with the prior terms. Whoops. So P of y is equal to 0. Let this be theta 1. P of y equals to 1. Let this equal to theta 2. How about P of y 2? Does anyone know what it is? Can anyone tell me, do we make this a parameter or what can we do with it? Yes, exactly, 1 minus. And since we're doing 1 minus, we don't really have to make another parameter for this. So for the prior terms, we just counted 2. All right, so let me keep track of that. Prior counted 2. How about for the class conditionals? Remember, let me write this formula up here so you guys can see it. P of x times P of x2 given C. And remember, x1 has 3 different states, x2 has 3 different states, and C also has 3 different states. So what do you want to do? Let's start with this one. This is the most complicated one. We have, let's start with x1 equals to 0, given a2, x2 is equal to a, and C equals to 1. That is one parameter, so theta, in this case, theta 3. How about P of x1 equals to 0, given x2 is equal to b? So we're incrementing this term right here, because later on we can just multiply it by 3 since we have 3 states for C. And that's this whole other parameter is equal to theta 4. And finally, 2 equals C. C equals to 1. Do we make this a parameter or we do the 1 minus thing again? Can anyone tell me? Exactly, because this term right here stays fixed. All right. And now we do the same thing for x1. So we counted 3 here, 3 here. So we do the same thing for x1 equals to 1, and then we'll count 3 parameters here as well. However, what do we do for P of x to 1 is equal to 2 in this case? What do you do here? Parameter or no parameter? Exactly, 1 minus. So from all that, we counted 3 plus 3. Are we done yet? Are we done yet with this term? Or are we missing something? It turns out we didn't variate the class. So we always had to fix that 1. But that's an easy fix. Because since it's in the conditional term, we can just multiply this by 3, like that. Also, give me a second. Gotta see if I made any mistakes. Nope. All right, perfect. So that's going to give you 18. All right. That's going to give you 18 different parameters for this conditional probability. So let's call this conditional 1, con 1. We got 18. And now for the next one, it's a lot easier. So we start with A, given C equals to 1, x2 is equals to B, given C equals to 1, and then P of x2 equals 2, C given C equals to 1. How many just from this? Can you guys tell me how many parameters are there just from this? Exactly, just two, because this is just one minus. Never forget that this is one minus um, P A minus P of B, where this is like P of A, P of B. All right, cool. And then can you tell me what do we have to do after that? Are we done yet? So this gives like two parameters. Set C equals to, whoops, yeah, I forgot to set C equals to 0. And then what do we do after that? Sorry, it was originally not supposed to be 1. It's supposed to start at 0, and then we basically increment this. So what do we have to do? Yes, times 3, because the C is in the conditional term. So we can't really cheat and do like 1 minus to get like only x2 times 2. So we do 2 times 3 by changing this term right here 3 times. All right. This gives you 6. So for the second conditional, we have 6. Add them together, you get 26 total parameters you have to learn. So yeah, if this question ever shows up, which it will probably show up, it's a very high likelihood, you guys will know how to do it without a problem. All right, time for the fun part, gradient descent. Which of the following is true or false? Justify your answer. Batch gradient descent should be used over SGD when your dataset is very large. Is that necessarily true or false? And this is for general cases. In general, should we use batch GD? Exactly, it's false. Can you explain why? Yes, that's correct, because it will take a lot of time. Sometimes might take you like a couple of days actually, because when I was training some of my neural network models, even with SGD, it took like, yeah, some if you have like a very big data set, even with SGD, it could take you like, I don't know, 2 to 3 hours for sufficiently large data sets. If you use batch gradient descent, it's going to take like a lot longer. I don't know if it's like double or triple, but in some cases it might take days, depending on your data set. Yeah, companies have a lot of data they're working with, and you have to use all of the data. Not necessarily all the data, but like a sufficient amount. Second part, SGD should be used in non-convex optimization. True or false? Think about what non-convex optimization is and what SGD does with its stochastic term, its random term. Remember, when you're training with an SGD, let's say this is your data set. Gradient descent is like this, right? It's like this. SGD, on the other hand, is like this. It's very spiky. And when you have like, say this is your curve, SGD is like it could jump like all over the place, here to here. So SGD should be used in non-convex optimization, true or false? It's okay if you're wrong, just do your best to answer and explain why. False because we can go in with our gradient. Um, I'm gonna answer the first one first. So for just gradient descent doesn't necessarily work pretty well with non-convex optimization because, like I said, If it were to be in like a local zone, a local minimum, then it will reach the local minimum. However, for stochastic gradient descent, now I'm not saying this is true for all cases, but like this is in general true. It would actually, because since if it like touches a noise term, if you use like a noise term in order to put into your stochastic gradient descent update function, then it could perhaps jump all the way to here. But it could also harm your algorithm as well. If your original weight was here, but then it suddenly jumped to the local, somewhere near the local minimum. So it's kind of like a double-edged sword, and you'll see that happen usually when you work with SGD. So in general, this is true, but overall it's not true. Still, you should use SGD over batch for non-convex optimization. Mini-batch gradient descent is faster than SGD and gives more stable convergence. Is this whole statement true or false? Let's say in general, is it true or false? Yes, you're correct. It is slower, but it is more stable. The reason why it's slower is because same reason why batch GD is. So can you explain number two again? Why? So SGD should it be used in non-convex optimization? For the most part, yes, because let's say you had like a non-convex function, right? So you had a non-convex function. Clearly, this function is non-convex. Do you agree? And let's say you initialize your point right here. You do not know what your loss function looks like. And then gradient descent would just converge to here. However, with stochastic gradient descent, remember, it jumps all over the place because it has like the stochastic term. And if it touches like if one of the terms is like very stochastic, it'll be like right here. It could jump like all the way to here and then converge to the global minimum. So the best diagram the professors usually show you is this diagram. This is like a levels, not really a level set, but like think of this as like a 3D surface. Then your gradient descent will converge to the local minimum, like this. Your stochastic gradient descent would look something like this. It would jump all over the place. And if you actually analyze the graph of SGD, it will it will look something like this, whereas GD is like this. By doing this, you can escape local minimums. But in general, this might not be true because let's say you started here and then you somehow jump to here and it converges. That's also a problem. So it's in general, it's true. Sorry, in general, it's not true, but most cases it is true. Does that make sense? Nice. Great. So, I believe you guys got this already. So it's basically the same reason why batch GD is slower than SGD, because you have to train it on the whole entire dataset. But in this case, we're training it on a subset, which is obviously slower than training it by just taking one point at a time. And obviously, it is more stable because we have a more averaged out update function because we're averaging it over more points. Batch gradient descent should oftenly be used over mini batch for small datasets. True or false? Keyword is oftenly. Yes, I guess. Can you explain why? Just just take a guess why we should use um batch oftenly we should use batch GD because mini batch might find a local minimum. Uh, that's actually the case for batch GD. Batch GD might land in like a local minimum as well. But The reason why we want to use batch GD over mini batch for small data sets is actually because since your data set is small, there's smaller cost to training time. Does that make sense? Because since our data set is very small, it, it doesn't take that long to train with the gradient descent algorithm. So the trade-off is made there. But there's not really any trade-off because your data set is very small, so it's fast. And it's more accurate as well. So in general, yes, you would use batch GD over mini batch. Perfect. Explain the primary difference between batch, mini batch, and stochastic gradient descent in write their update function. So let's start with the first part. Can anyone tell me the difference between batch, mini batch, and stochastic? I think I already explained much of the differences, the primary differences in the previous question. But can we just reiterate what they were? I'll give you guys a couple of seconds to type it in the chat. Yes, that is a perfect answer. And for batch, since we're taking the whole data set, and let's say our initialization of the weights is fixed. In that case, batch is deterministic, whereas mini batch and stochastic gradient descent, as their names imply, are non-deterministic because we take a arbitrary subset or an arbitrary single point. All right. As for writing their update function, I think that's pretty easy, so I'm just going to show you guys. So for batch gradient descent, theta t plus 1, so your update is equal to the previous theta minus alpha. Remember, alpha is your learning rate, times the gradient. So this is math cal j. And in here, you want to have, it's a function of theta, but then you're also given the whole entire data set. So 1 through n. And also your labels or your output, your target values, y, evaluated at theta t. All right. This is batch GD. For mini batch, can anyone tell me, can anyone just briefly describe what goes here? Change k n to k. Yup, that is correct. K. Where k is less than n. That is correct. Sorry if this is unclear, but I hope you guys get the point. Where k is strictly less than n. Otherwise, if it's equal to, then it's just batch. All right. Also got to mention, before doing that, you actually need to shuffle your data set as well. Just so that you don't always get like the first K terms, you actually get a random sample. And I think that might be helpful for the last bonus question I had right here. Write pseudocode for it. I'm not going to cover this because I might not have enough time, but you guys should definitely try this question out. And finally, for stochastic gradient descent, it's literally the same thing. Literally the same thing. Except what goes here instead? Does anyone know? Does anyone know what goes into these slots? Yep, xi and yi, because we're just sampling one point for it. All right. And finally, for the last, is this the last question? Yep. Finally, for the last question. When performing mini-batch gradient descent at some epoch, you observe that the loss function suddenly spikes up before converging to a local minimum. What might be a possible cause? So what might be a possible cause? And how can you fix this? So just to visualize this, when performing, you observe that the loss function sum by some converges. You know. Let's say your loss function is like this. It's decreasing, but then suddenly it jumps up like this. Sorry, that's not proper. It jumps up like this, and then it converges. Can anyone tell me overshoot? Yes, it overshot, but what might have caused it? Non-convex data. Exactly, that's one thing. It's something, there's also something that got to do with the mini batch GD as well. What about the mini batch GD? Learning rate is too large. That could also be one problem. I'm looking for a very particular one related to mini batch gradient descent. But you're correct. The new subset of data. Yes, exactly. The subset of data. What about the subset of data? What might be contained in that new subset of data that might cause your loss function? So let's say this is the graph of your loss function, and it's right here. Sorry, it's right here. It was converging uniformly until, boom, it's right here. So what might that say about the size of the subset? Remember, when you're increasing the size, you're increasing like the robustness. It's less sensitive to outliers. When you decrease the size, there's more outliers to relevant data portion. So in this case, your subset might be too small. But all of your answers are correct. That's just the one I was looking for. So did everyone get that? So that your mini batch gradient descent subset is way too small. So what you have to do, how can you fix this? You increase it so that it has a more stable convergence. That's what I think that's what Irene said. If you increase the set size, then it's more of a stable convergence. Yeah, in general, that's true. All right. Okay. And that brings us to the end of the review seminar. But let me just point out this question for you guys. This question is just basically telling you to use mini batch GD to find the optimal solution to logistic regression for binary classification. Note, this question is not too much different from just batch gradient descent used on OLS. All you have to do is just change up the objective function and do not forget to shuffle your data set. And also the loss function for the gradient of the loss function of logistic regression. I believe that's already given to you. I'm actually going to give you to you right now. Just in case if this actually shows up on the exam, it's equal to yi minus pi xi, where x is a vector. All right. So this is the gradient. It's the gradient of the loss function. Yeah, where pi is equal to 1 over 1 plus e to the w transpose xi plus the beta term. Okay? And you're trying to find the objective function with respect to w. So with that in mind, I hope you guys have a great day, and I wish you guys the best of luck on your second term test. All right? Thank you guys so much for coming to the review seminar. Can we see the eon again? I don't understand. The equation. Oh, sure, absolutely. It's in your lecture notes, I think. It's in your lecture notes, so you could probably just pull it up and refer to it. But I'll be posting the slides and the solutions later. Here, I'll actually post the solutions in the chat right now. Or actually, no, it has some mistakes in it. I'll post it in the AMACSS. All right. If anyone has any questions, I'm here to stay for a bit. And see you guys later.